Hi everybody, it's Gavin again, and today we're going to be talking about the Maglev train. Maglev, Maglev. Um, my portion of the topic is all about the history and science behind it, giving an explanation of how it works is somewhat of a difficult one because there aren't many out there. So, in terms of recommendations, it hasn't had enough worldwide experience, and the um, idea of how it works is also a little difficult to explain. Due to the fact that a lot of it is very technical and it is easy to get lost and therefore making it hard to be presented in a simple and understandable manner. Um, so I'll try to explain it the best as possible. If you have any questions, please feel free to message me with those questions, and I'll try to my best to get back to you and answer you with the best easiest possible answer. Now, before I start talking about the maglev trains and how they work, I'd like to give a dive into the history, so to speak, of how the maglev train and the development into magnetic levitation as its application in the modern transport system transport system. Finally, I'll try to give you the actual answer to how maglev trains work. So, without further ado, let's get into it. So the fastest maglev trains achieved an astonishing speed of 603 kilometers per hour, so which converted into how we measure speed, it's roughly 374 miles per hour. So in comparison to speed, that's pretty fast, so to speak. Um, this actually happened in Japan along the Yamanashi line in April 21st of 2015. But besides speed, these trains are super interesting due to the fact that they actually levitate above the ground. Now, this isn't, Harry Potter or the futuristic flying car where, it'll take off and fly you to work or whatever destination you desire. But basically, maglev can be defined as a system that enables a train to repel and push off the track, while at the same time, um, enables the train to move in such elevated conditions, taking advantage of the lack of friction that there is within the train tracks. This lack of friction is a direct cause of several advantages that maglev trains have compared to conventional and high-speed railway systems. Due to the fact that there is no need for moving parts, such as axles and wheels, maglev trains have longer life cycles and low operating costs, higher energy efficiency, and at the end they are very clean and quiet and capable of developing higher speeds due to not having to work on the more mechanically motorized side of things with having to have, the axles, the wheels, all the parts that really define and characterize, most trains in our day-to-day age. Their main disadvantage, though, is much higher construction cost, which is in some cases 2 to 3 times higher than in the case of high-speed railway systems, and about 60 times higher than in the case of conventional railways. Besides the cost of construction, another fact to consider is the fact that maglev trains really require the use of a lot of rare earth elements, which may be quite expensive. And knowing that, this whole entire train operates off of magnets. The word maglev is, a combination of the two words magnet and levitation. They shortened it and put them together using the first three letters of each word, so mag and lev. But before we take a dive, let's explain how this actually all began. The fundamental ideas that led to the creation of maglev technology started developing at the beginning of the 20th century. Um, Actually, several different patents and inventions had to be made in order to make possible movement of trains using magnetic levitation. Um, the history of linear electric motors, which are tightly bound to the modern maglev trains, can be traced back to at least the middle of the 19th century and the 18th century. I got those two backwards, but the 18th and 19th century, roughly between the middle of the 18th all the way dating to the 19th, there was a lot of patents going on. However, all such models were inefficient. It was only up until 1902 and 1907 when the German inventor Alfred Zuden, uh, I'm probably mispronouncing that due to it being a German name, but otherwise, he submitted two patents for the first linear motor propelled train. Linear motors are, in fact, a type of electric motors that have its stators and rotors sort of unrolled in a sense. So instead of producing a rotational movement, um, the rotational movement, they produce a very linear force along their length. In a linear motor, the electrical energy is converted to a linear mechanical energy with high efficiency, which is done through the electromagnetic interaction between a coil and a permanent magnet assembly. Okay, that's just one piece of the puzzle. Um, so with this idea of the linear and how everything is somewhat unrolled, it goes through the whole entire train so that it is in a linear plane to the actual tracks. In 1908, the Cleveland mayor Tom L. Johnson filed a patent for a wheelless high-speed railway levitated by an induced magnetic field. Um, After that, we had a series of patents for magnetic levitation trains propelled by linear motors, such as those made by Robert Goddard, Emile Bachelet, and Hermann Kepler during the 1930s and 1940s. So after the first idea of the patent came out, everybody started looking at those and gave their own idea slash patent for this idea using the magnetics to use a sort of push-pull base space between, the track and the train without having to actually have wheels. Keep in mind, all these were only ideas, drafts and patents with the expectation of Hermann Kemper's invention, who constructed a first working circuit hovering on the principle of electromagnetic levitation. However, in the late 40s, 1940s-ish, the British electrical engineer Eric Laithwaite, a professor at Imperial College London, developed the first full-sized working model of a linear induction motor. Since we have indicated, linear motors don't require physical contact between the vehicle and the guideway, they became a common fixture of the experiments relating to the advanced transportation system. One such project was so-called the tracked hovercraft. So it was, hovering above the tracks. It was an experimental high-speed train developed in the UK during the 1960s, and it's combined two inventions, the hovercraft and the linear induced motor. In an effort to produce a train system that would enable 400 kilometers per hour passenger service and with lowered capital costs. However, though, the tracked hovercraft was canceled as many other similar projects as part of the budget cuts in 1973. Finally, in the early 1970s, though, the already mentioned Professor Eric Laithwaite had discovered something which might be described as the final piece of the Maglev puzzle. Um, in its essence, it was a new and special arrangement of magnets in science known as the magnetic river. The invention allowed single linear motor to produce both lift and forward propulsion, allowing a maglev system to be built with a single set of magnets. And so I did draw up a somewhat form of this. We have magnetic field lines, and these are both the opposite poles attract and like poles repel. So here's that. Based on this, they attract each other with the like poles, and just as the opposite, we use the repels of like magnets to repel each other. And so with these became the idea of the um, magnetic river. Um, um, this invention allowed single linear motors to produce both lift and forward propulsion, allowing a maglev system to be built with a single set of magnets as shown. And because of this breakthrough, Dr. Lathwaite became known as the father of maglev, although maglev have been developed and studied for more than half a century. Since the invention of the magnetic river, only a few countries today have the capacity to implement this technology um, and practice. Furthermore, the only countries that have studied and tested the maglev technology so far are the UK, the USA, Japan, Germany, USSR, Russia, so pretty much, China, and South Korea. So that's about 7 countries so far. And in order to really explain how maglev works, we must understand some basic concepts of physics. And these were the countries that were primary proponents in the ideas of physics and learning the next best thing. Um, in this first line, concepts of attraction and repulsion, as I've shown, of magnets, but also the concept of electromagnetism and superconductivity. Um, since pretty much everybody understands with the same poles of the magnet oppose while opposite ones attract each other, we will briefly introduce the two remaining terms. First one is electromagnetism, one of the four fundamental forces of nature. Let's see, nature. What is even more important, though, is electromagnet is the object that creates a magnetic field. When electric current flows through it, it is usually simple conductors such as wires or cables, or even a better, the combination of iron core and a wire wrapped around. So I drew another one for this. So here is a iron core with a wire wrapped around it, and the direction of current determines the electromagnet's polarity. And in addition, if you change the direction of currents, so if you're going from this side and you change the current, so you swap this, the S and N of the magnet polarity, everything completely changes and goes directions. Put that somewhere in your notes if you have any more questions about that. Our second term is superconductivity. Superconductivity is a property of a complete disappearance of electrical resistance in various solids as they are cooled below a characteristic temperature. So using cooled magnets, in a sense, is the study for this. This temperature varies for different materials, though, but in general, it's below 20 degrees Kelvin. As superconductive magnets are super strong and super efficient, they are generally used to generate powerful magnetic fields, which have the ability to levitate and propel the train. Now, maglevs, there are two main types of maglev trains. Those electromagnetic suspensions uses the attractive force. Two different, levitations. I got a little confused in my notes. So the two main types of maglev trains are two different forms of electromagnetic suspension, also known as EMS. and those based on electrodynamic suspension, also known as EDS. Um, both types have similar propulsions and principles based on the linear motor, while the main difference is in the way how levitation is achieved. Electromagnetic suspension uses the attractive force between electromagnets present underside the train and the magnets present on the guideway to levitate the train. This attracting force keeps the train about 1 to 2 centimeters above the guideway. Bear in mind it is strong enough to overcome gravitational force, though. Um, the stabilization of train is achieved with the help of side guidance magnets. So with that, it's somewhat of a picture right here. So the train goes over the rails and there is a side guidance of magnets. Um, And so this propulsion is secured by a constant changing polarity, as I showed right here with different magnets that change constantly. Um, they change the magnets along the track, which, speaking in terms of linear motors per se, acts as a stator, so the opposite for what most trains are needed when running down the tracks. In that way, the electromagnets on board, which act as rotors, change the current forward along the track. In that way, though, the train moves forward. So by switching polarities constantly, it's a push and pull repel kind of form, which pushes the train forward. Um, while the speed is controlled by changing the frequency of alternating currents. So having in mind that magnet attraction varies inversely with the square of distance, minor changes in distance between the magnets and the rails can produce greatly varying forces which can change the speed at which the train moves. These changes in force dictated a need of sophisticated feedback system, though. This feedback system, which maintains a constant gap of approximately 8 to 10 millimeters, this method is simpler to implement than the electrodynamic system that I talked about just a second ago. And it also has the capability to maintain a levitation at zero speed, so which is not the case with the EDS. So with the EDS, you have to keep a constant speed, which would really require the use of wheels to help move it forward until it reaches the speed at which it can take the wheels back up into the train like an airplane can. And yeah, with the EDS, it can stay levitated above the tracks, even if it's just sitting still. The repulsive force is high enough to overcome gravitational force and allows it to sit about 10 centimeters above the guideway when a train moves along the track. The supercooled superconducting magnets in either side of the train, just right here as I showed in these, will be on the sides. And so they're located on the sides of the train. And we would need to have an induced electric current of the levitation coils and create a magnetic field. Levitation coils are located on the guideway, so the train tracks. And they have the shape and figure of a figure 8 so that it can constantly switch through the polarities in a sense. When these coils experience the changing magnetic field made by the moving superconductors, two currents are induced and the oppose the change in the magnet field. So with that, based off that picture, the two combined are responsible for levitation of the vehicle. Let's see, let's just skip down to, the benefits of this method are incredible stability at high speeds. And so Based off other trains, the trains we have now in America, all it takes is for the trains to reach a high enough speed, and it's an easy derailing. But based off the magnetic physics and all the stuff that I just explained, which is a little confusing, it can reach super high speeds, as I stated up above, with the highest record speed, without having any chance of derailing due to the super conductivity of the railroad tracks, keeping it super magnetized to each other, therefore making it an easier and safer way of travel. And the bad side, though, is the fact that the sufficient speed must be achieved in order to levitate the train at all. For this reason, the train must be equipped with wheels, or some other form of landing gear in order to support the train until it reaches its takeoff speed. Except for, that type of suspension, maglev trains can be divided between low-speed maglev trains, which have a maximum speed of about 100 to 130 kilometers per hour, and high-speed maglev trains having a maximum of 400 to 500 kilometers per hour. 6 commercial maglev systems are currently in operation around the world. So out of the 7 countries that had done the research on maglev physics and the stuff about it, we only have 6 places around the world that still have and continue to broaden the horizons by making more maglev trains. One is located in Japan, 2 are located in South Korea, and the last 3 remaining are in China. With that, now we see that there aren't very many places that have maglev trains. Yet America was the first leading place in discovering maglev technology. So I believe, with this, we should probably try more to broaden our horizons and make more of these, even at the cost and expense of super expensive recreation of railroad tracks. But it would help to bring down the costs in repairs for our railways, and helps make a safer and easier traveling instead of the anxiety-filled airplane rides. This draws my presentation to an end. I hope you guys enjoyed learning about the maglev trains, even though it was very confusing having to learn all this physics and stuff like that. Thank you for bearing with me for this amount of time. And thank you, and I really hope you enjoyed learning about what you took from this lesson slash, talk about maglev trains and where they came from. And I thank you again for watching.